My today's topic is about the detection of gravitational waves, and the method I have chosen here is a laser interferometer. Now, to begin, at first, we have to know about what gravitational waves are. Back in 1915, Einstein published his own theory of gravity, that is, general theory of relativity. It's a beautiful idea which tells us that gravity is nothing but those warps and curves in space-time fabric. Now, barely 1 year later, Einstein also realized that if space is flexible enough to warp, then it should be able to ripple, to vibrate, to undulate. And those ripples, we are now call them gravitational waves. As you can see in that particular animation. Oh, come on, I cannot show you the four-dimensional waves in just particular two-dimensional screen. So don't bother about that. Okay, now, of course, by jostling my hand into the space, I cannot produce such detectable gravitational waves. Rather, calculation shows if two heavy objects like two black holes or you can say two neutron stars, as they orbit to each other, as you can see, they jostle the space-time right that particular amount to produce such detectable gravitational waves. And math also shows that as those waves rolls by, they can stretch and squeeze anything on the path of them. But I want to emphasize one thing that is not to scale. Those stretches and squeezes is just of the order of a fraction of nuclear diameter. And that is pretty challenging for us humans to detect such tiny variations. And that's what our LIGO team did in 2015. And that is pretty remarkable in the history of science. They are introducing a prior concept that is Michelson interferometer. So here it is. What is that? There is a laser which shoots the laser beam, which comes out to that particular beam splitter, which splits the laser beam into two part. 50% of the light goes through this arm and the remaining part goes to that arm. They reflects back from the mirror and recombines at the beam splitter where they form an interference pattern, and by studying those patterns we can calculate the effect of gravitational waves. So let me show how LIGO works. LIGO shoots a laser beam from their main building, which comes to the beam splitter and splits into two parts, goes through those long two perpendicular arms having same length, and recombines at the beam splitter again, where they cancel out each other. That means no light is now being detected to the photodetector of LIGO. So you may thought there should be an interference pattern, but I clearly see there is nothing. So let me clarify that thing too. There surely be an interference pattern forming by those two beams, but the photodetector of LIGO is placed in such a way that it only focuses upon only one particular dark fringe over the whole variety of fringe patterns. So, as the story goes, as gravitational waves passes by the Earth, it stretches and squeezes the space-time near the Earth. As you can see in that particular animation, it is vastly exaggerated as you can see. But as those waves passes by, they results to the arm lengths of those interferometer. That means now those arm lengths are not being same enough. That means some of the light is now being detected to the photodetector of LIGO. Those light waves is now not aligned at the particular way where it does, and the subtle change in the fringe pattern is now being observed in the photodetector of LIGO, and that is an indirect proof of existence of gravitational waves. So let me go through some calculations. So power measured in the photodetector comes from that particular relation, that is this. As you can see, there is a term in the right hand side that is Ly minus Lx called the length variation. So any variation of length of those two arms can result directly to the power output of the photodetector. Now, I want to grab your attention to a particular term that is polarization. So, what is that? Polarization is the geometrical orientation of waves. For electric field, there is vertical polarization and horizontal polarization and so forth, as you know. And electromagnetic waves are actually the oscillations in electric field and magnetic field vectors. And the polarization is the direction of electric field. For gravitational waves are the oscillations in metric perturbation, that is h mu nu, and the polarization is the direction how the distance changes between 2 points. Gravitational waves has two polarization, that is plus polarization and cross polarization, as you can see. So don't bother about those particular thing, plus and cross marks and all those things. They are just matrices like this. Plus polarization corresponding that particular matrix and cross polarization correspond this particular matrix. As you can see, the traces of those matrices are zero. That's why it is called transverse traceless gauge. Okay, so what is gauge? Let me clarify you. Gauge is a choice we have the freedom to make, and that doesn't affect our physical system at all. So, by choosing a gauge, that particular gauge for our case, that particular gauge, that is Lorentz gauge, by choosing that particular gauge, we can reduce the left hand side of the Einstein's field equation. As you can see, there is a term that is G mu nu. That is the left hand side of the Einstein's field equation. By choosing the Lorentz gauge condition, we can calculate that the first three term goes to 0 and the G menu only left over with the box of H menu. And by implementing the vacuum condition, that is T menu equals 0, we can calculate a wave equation, that is box of H menu equals 0. By solving that particular wave equation, we can get another relation, that is this particular thing. Now we are considering only the plus polarization, of course, for the simplicity. Now going forward, we can write the spacetime interval in tt frame in that particular manner, and as we know, the photon travels to null geodesics. By implementing that thing, we can calculate this to that particular term. Okay, now knowing some time instances like the time when photon reaches to the beam splitter and to the mirror, we can calculate how much it travels from the prior relations, and we can also calculate for the return tip too. And by doing some mathematical jumbling, we can calculate the time differences measured by our clock to get those two trips. And we can also calculate the same thing for the YM2. And by knowing some two time instances, that is when it comes to the returns to the beam splitter for X arm and Y arm, we can calculate the electric field for the X arm and Y arm repeatedly. Okay, now, there's a two phase differences we are observing in those EX and EY term. As you can see, they are actually the phase differences introduced by the gravitational waves. So there is a total phase difference called delta phi mc that is there. So by knowing that particular relation, we can calculate the total electric field in that particular manner and total power output by this particular manner. As you can see now, the power output of our photodetector is now being related to the total phase difference, that is delta phi mc. So we want to have delta phi mc as large as possible. Now by implementing that condition, we can calculate the arm lengths of those two perpendicular arms, that is 750 kilometers per 100 hertz frequency range. Okay, to sum up all those things, to observe the effect of gravitational waves, to observe the sufficient effect of gravitational waves, I'd rather say. Okay, for that particular reason, we have to build a 750-kilometer long arm length for this interferometer. And here is a catch: we just cannot build such long arm lengths on the surface of Earth, as the curvature of Earth comes into the picture. So, what to do? There is a solution regarding to that particular problem, so I don't want to deep dive into that particular thing as it not related to my that particular project, but I can give you some glimpse of that particular thing. Now by introducing every parrot cavity, what is that? There is a two mirror introduced in those perpendicular arms. By introducing them, we can bounces the light beam back and forth many times between those two mirrors. And by doing this, we can mimic a bigger arm length by making a much smaller omelets on the surface of Earth. And that's how the problem gets resolved. So, finally, why should we detect them? In this case, my first point is like it is like a new organ for us to sense the universe. So, suppose I only have eyes and nothing else. That means I only can sense electromagnetic waves from different visible frequency light range. And whenever I have ears, I can also sense those longitudinal waves, that is sound waves. That means having another organ, I can sense more information from the nature. And from the past decades, we are only using the electromagnetic waves from different frequency range to visualize or to picturize our universe. But whenever we detect gravitational waves more and more, we can also get information rich about that particular source, and we can calculate the more vastly picture of our universe. My second point is it carries the information about their origins is free of the distortion and alteration. That means when gravitational waves travels, it has no distortion at all because it travels through the space-time itself. So there's nothing to distort its signals. And my third point is it can may give us a clear view of the gravitational wave universe. So what is that? So there is a beautiful picture out there that is cosmic microwave background. Yes, I called it a beautiful picture for me at least. CMB. Okay, what is CMB? CMB is a heat left over after the Big Bang. But there is a limit for that. Prior to that particular condition, there is a opaque universe, opaque baby universe, from where nothing, not even light, can escape from it, except gravitational waves. So, by studying more and more gravitational waves, we can calculate the prior conditions of our baby universe and we can look further for calculate our initial conditions of the universe. Okay, so that's it. Thank you for listening.